All right, this is Mr. McCord's ICP class, Unit 4, Lab number 2, Metals, Nonmetals, and Metalloids. So on the periodic table, we've got a whole slew of elements, right, that we can arrange in different ways. The periodic table is arranged in this way for kind of our purposes, so we can easily track down information like how many valence electrons something will have, or something like that, how many protons it has in an atom. But also, we have information about the characteristic of the element itself that can be really helpful for predicting how an element's going to act, what it behaves like in the real world. So, for instance, metals are something we are pretty familiar with in our everyday life. Typically, we like them because they are shiny. All right, we say in sciencey terms that things have luster when they are shiny, so this is very lustrous. All right, great for jewelry and all your bling. All right, that is also flexible. All right, there are kind of two kinds of flexible we talk about with metals. Malleable means we can hammer stuff out into thin sheets, like this guy right here. And ductile means we can run stuff into thin wires, like this copper right here. All right, both have to do with the fact that metals are workable. Even though they are durable physically, we can still change their shape around pretty easily. They tend to have high melting points and even higher boiling points. Okay, there's only one metal in the periodic table that is liquid at room temperature, and that is mercury. Gallium is a close second, but it takes a little bit of heat compared to room temperature to melt into a liquid. But most metals are pretty hardy. They hold up to the heat and the temperature pretty well. Okay. We also have some metals that are magnetic. Right, so I've got the end of a magnet on this flashlight here. All right. Not every metal is magnetic. This pan is metal, but it's not magnetic. This piece of plumber's tape is magnetic. Copper wire, no. It's brass, not really, no. Mercury, no. So just because something's a metal doesn't necessarily mean it's going to be magnetic. But that's where we usually find magnetism, is in metals. All right? Now, we can also find them out in the real world, the natural world. So this is a piece of what we call native copper. This is how it looks when you kind of mine it out compared to what we transform it into for our needs. But not all of the elements that we deal with are metals. We have quite a few nonmetals that take up the right side of the periodic table over here. A lot of them are also solids, but we have a few gases in here naturally, like helium and neon and argon and krypton. Fluorine and chlorine are gases at room temperature. Bromine is a liquid at room temperature. And then we've got a bunch of other solids and stuff here too, aside from nitrogen and oxygen and things. Okay. So nonmetals are basically what metals aren't. So if metals are shiny and they're lustrous, then nonmetals are dull. If some metals are magnetic, then we're probably not going to find any magnetic nonmetals on the periodic table. If metals are flexible, all right, malleable or ductile, then nonmetals are probably going to be brittle. They're easy to break. They don't flex very well. And something else about metals is that they are good conductors, not only of electricity, like what we tend to use copper wire for a lot of times, but also for heat. They heat up very well, which is why we use them in cookware like pots and pans. All right. On the other hand, nonmetals are bad conductors, or what we call poor conductors. They don't transfer electricity or heat very well at all. They're kind of like insulators. They keep heat from moving. They don't transfer very well from atom to atom. Okay. Now we also have a class of elements that's in between, called the metalloids, that share some properties of both. They're not really a metal, they're not really a nonmetal, so rather than trying to pick one or the other, we gave them a new category. So in this lab we'll also see some examples of what that could be like, and kind of that mixture of properties, what it ends up with. All right, at this first station, we have 4 elements to look at. We have a piece of lead, all right? Chemical symbol for that is Pb. We have zinc, symbol for that is Zn. We have carbon, symbol for that is C. And then silicon, symbol Si. So, just to kind of get a look at them, they're all kind of grayish or darkish colored, which we tend to see for a lot of metals, except for a few standouts like copper. All right, so just looking at them, it's kind of hard to tell. They could all be metal, maybe. So we have to test their properties a little bit deeper. So they're all in the solid form. All right, solid, 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 and this is what silicon looks like from the other side. Okay, we could check their conductivity to see whether they conduct electricity or not. So I've got a little pilot light starter thing that I can use to kind of zap these and see if a spark travels across to see if it is conductive or not. We can test to see if they are magnetic or not. I've got my magnet again here. Okay, lead is not magnetic. Okay. Zinc is also not magnetic. Our silicon, also not magnetic. And carbon, not magnetic. So none of these elements are magnetic. But I'm sure at least one of these has got to be a metal. So not all metals are going to be magnetic. We're going to have to look at some of the other properties to kind of narrow it down even further. Now, metals should be pretty bendable, so you can even see this piece of lead has already kind of been tearing a little bit because it is quite bendable. It's actually a very soft metal, right? Which is what made it good for, old pencils instead of what we use today, graphite. Now, graphite is actually carbon, this other thing right here. In fact, I'll bring this paper over here. It's not very good at doing it, but I can write with it. Typically, if we want it to work better in pencil lead, we add a little bit of clay so it runs a little bit smoother, breaks off a little bit easier. Okay, but carbon, graphite, is what we use in modern day pencil lead, quote unquote lead. Okay, now these other guys, they're not going to flex. This one's not going to flex, and it's probably actually going to break. I don't want to push it too hard. You can see on the end there, it's kind of fractured a little bit from where it was broken off before. So this is definitely not flexible. So our silicon and our carbon are probably more like nonmetals compared to the zinc and the lead here. So if I had to take a guess, I'd maybe put these two as metals and these two as nonmetals. Okay. But for our conductivity, silicon and carbon both conduct electricity. Right? I haven't tested them for heat conductivity, but the electrical conductivity is a pretty good sign that there's something going on here. So carbon is an oddball case. It is a nonmetal, but it is close to the metalloids. Silicon is one of those metalloids. Carbon and silicon both conduct electricity, so they kind of ride that boundary between metals and nonmetals. Now, carbon has too many properties that make it act like a nonmetal compared to silicon, so we do shove it over in the nonmetals category. But silicon is just on that boundary enough to be shiny enough and to be conductive enough that it's not quite a nonmetal, it's not quite a metal, so we call it a metalloid. So here's something that's interesting.
Carbon, silicon, and lead are all in the same group going up and down here, the same family, even though they're in different periods of the periodic table. We have a nonmetal and a metalloid and a metal all in the same group. Zinc is kind of over here off to the side. So carbon and silicon and lead are all in group 14. They share that in common, but they're in different periods. Carbon is in period 2, silicon is in period 3, and lead is all the way down in period 6. And then zinc is over here kind of on its own in period 4 and group 12. Remember, group 14 with carbon and silicon and lead is also called the carbon group because carbon tops it all off. And we don't have a specific name for zinc's column. It's just in the section we call the transition metals from column 3, from group 3 to group 12.
Okay, station 2 is a little less exciting because each of these elements that we're dealing with, helium and oxygen and nitrogen, are all gases. They are all colorless. They are clear. They don't have a color. We can't see them. They're invisible. Okay, so the only place on the periodic table we have gases is in the nonmetals section. So these kind of have to be nonmetals. We could try to test them for, magnetism or something like that, but even if they were moving around from the magnet, we wouldn't be able to see it. Conductivity is also kind of not a thing we can do. However, oxygen and nitrogen make up most of the air that you breathe. Sparks can travel through air, but not super well. So they're not very good conductors. And if you've ever had a good thermos or a nice woolly pair of gloves, air is a lot of times used as an insulator in big heavy jackets or in thermoses and things like that. You have a layer of air either in pockets of fluff or inside the walls of a thermos or an insulated cup to keep heat from moving in and out. So poor conductor means that these have some more evidence that these are nonmetals.
Unlike with station 1, here we don't have any elements that are in the same group, the same family, the same column with each other. But we do have two elements that are in the same period. Nitrogen and oxygen are in the same row. They are in row 2, so the second period of the periodic table. Now, that doesn't say as much about sharing properties, but, it is a way to kind of categorize them. Helium is over in period 1 with hydrogen, and hydrogen and helium are the only two in that row. So just because there's a gap doesn't mean they aren't included in a row. It's not like we have to worry about making this separate from this. They're the same going across. Nitrogen and oxygen are in the nitrogen group and the oxygen group respectively. Again, not really clever names for those. All right, and helium is in the noble gases group. Helium is in the noble gases group.
All right, at station 3, we have 4 elements: iron, aluminum, nickel, and copper. This is our iron here, Fe. This is our aluminum, Al. This is our nickel, Ni. And this is our copper over here, Cu. Okay? So these 4 metals are probably ones you've heard of before and can identify as metals just by the name of it. Like iron is going to be a metal. Aluminum, you've probably heard of from aluminum foil. All right. Nickel, from the coin. And copper, with its characteristic orangish, kind of shiny color there. Okay, now we can of course still test them for properties of metals, like how flexible they are. Now in this case, this piece of iron is way too thick to be flexed, so I'm not going to worry about it for this one. So I'm just going to compare the two metals that can be flexed. So I've got aluminum here, which is pretty flexible, pretty easy to bend. And I've got copper here. It's about the same thickness. and it's a little bit tougher. It's a little bit harder to flex that. Okay, now copper is, of course, very ductile because it can be drawn out in these thin wires, so it kind of has that going for it. They are all, relatively, kind of metal colors that we would expect. They're shiny, at least in places where the rust hasn't gotten this iron block. See if I can get to cast the light there for the camera. So we got kind of a grayish color where there isn't rust. We've got kind of a grayish color, kind of a grayish color. This piece is nice and polished, so it's lustrous and shiny. And then copper is one of those weird metals that doesn't have that sort of grayish color, but it is still lustrous. It is still shiny. I could maybe shine that up a little bit more, but not too bad. We can test it for conductivity. All right, so I can get my conductivity tester. Go try each of these. So you can test iron to see if it's conductive. Test aluminum to see if it's conductive. You can test to see if nickel is conductive. And we can test to see if copper is conductive. We can also check for magnetism. Oh yeah. Iron is the kind of big player in magnetism. A lot of alloys, mixtures of metals that are magnetic, have iron in them. So if you are just sticking your magnet on something and it sticks, there's a good chance there's iron in there. But it's not the only magnetic metal. It's just one of a handful. Aluminum is not one of those metals. If you take a piece of aluminum foil and stick a magnet on it, it's not going to really do much. Nickel is magnetic. Now you might have to have a nice piece of it that's kind of got the polish on it, but nickel is magnetic. And copper, not so much. Okay? In some cases, it's good to not have something magnetic still be a metal, because we can have something that is sturdy but isn't swayed by magnetic forces and things. When you have machinery that operates and uses magnets, sometimes you don't want something that can be pushed or pulled by that magnetic force. So using something like iron or nickel is not always kind of the best deal for that, especially when you have other materials that are more flexible or more easily changed into wires. Based on how these look, you can decide for yourself which one of these is the most lustrous, the most shiny.
If we look at the periodic table, iron, nickel, and copper are all in the same period. They are all in period 4, despite being in different sections of the transition metals. So we've got like irons in group 8, nickels in group 10, coppers in group 11. They're all in the same period, so they have that in common. Aluminum is not in the same group or period. Aluminum's in the 13th column, which is the boron group, headed up by, of course, boron. But it's still a metal. It's close enough to that kind of left side to be included there. All right, and if we track it over to the left, aluminum is in period 3 of the periodic table.
In station 4, we have 4 elements. We're looking at sulfur, which is the sort of yellow stuff here. We've got tin, right here. We've got silicon, which we saw before, station 1, and magnesium. All right. We've got these samples in jars here. Sulfur is not good to breathe in. All right, the dust is kind of harmful to you, so we're going to leave that one in the jar, so we're not going to test it for conductivity and magnetism. But, spoiler alert, it's not conductive, it's not magnetic, so we're not really missing out anyway. Okay, take a little bit of our tin out. Leave it by that jar. Take some silicon out. And our magnesium. There we go. Okay, so just by looking at them, we've got two things that are kind of this classic grayish, shiny-ish, lustrous kind of look, like we would expect from metals. Silicon also kind of has that luster, which we talked about before, but it's kind of a little more of a bluish gray than just a straight kind of metallic gray. Sulfur is yellow, which really stands out. It's also soft and powdery. This is standing out not as a metal, but as a non-metal. It's very not metallic. Even as a dust is still a solid. It's just very, very small pieces of a solid. It doesn't flow. We can shift it around, but it's not quite what a liquid would be. We could still melt it. So all these are solids. We can test for conductivity. So we can test tin to see if it's conductive. We can see if silicon is conductive. We can see if magnesium is conductive. We can also compare how lustrous they are. So this is the tin, and this is the silicon, and this is our magnesium. We can test for magnetism. Ooh, oh, I think I grabbed the lid. If I take just a piece of tin out of here, not really. Don't really have any magnetism going on there. About silicon, that's a super small piece. Okay, silicon, no, dud. And magnesium, nope. So none of these are magnetic.
Out of these four, three of these elements are in the same period, the same row on the periodic table. Magnesium, silicon, and sulfur are all in period 3 going across, but silicon and tin also are in the same group going up and down. They are in group 14 with carbon, and we call that the carbon group.
In station 5, we have three elements: hydrogen, cobalt, and gallium. So out of these three, hydrogen is pretty easy to knock out. It's probably not going to be a metal because it is a gas. Hydrogen is a gas. It's colorless. Right? Doesn't have a color. It is invisible. It's see-through. It's clear. And it's gaseous. So it's very likely not a metal. It's going to be a non-metal. Cobalt and gallium, on the other hand, are both pretty metallic looking. They're kind of this grayish color. They've got a little bit of shine to them. Gallium's maybe a little bit more lustrous than my cobalt here. But there are other ways we can test these properties as well. I can test these for conductivity. So I can see if cobalt is a good conductor of electricity, and I can see if gallium is a good conductor of electricity. You can find videos online of gallium melting in just the warmth of your hand. Its melting point is very low compared to other metals. We can test them for magnetism. So my gallium, not magnetic. My cobalt, is. Cobalt is one of the rare elements that actually is magnetic on its own without having to be mixed with iron. So cobalt is magnetic.
Not much exciting here. Cobalt and gallium are in the same period, period 4, but other than that, they aren't in the same group, and hydrogen's in neither the same group or the same period. Hydrogen's kind of all on its own over here in the alkali metals group, whereas cobalt is in the transition metals section, and gallium is in the boron group.
All right, at station 6, we have cadmium, mercury, and zinc. Cadmium's here, zinc's here, mercury is in here, and it's also in here. Just by looks, Cadmium and zinc are pretty good candidates to be metals. They're gray and shiny. Looks like maybe they can be worked into different pieces. Pretty flexible. These guys have been pushed into pellets. Okay, mercury might be a little odd because it's a liquid, but it is a metal. It's not very safe. The vapors can be really bad for you, as well as organic compounds involving mercury. But I'm just going to say it's a metal here, and we want to worry about trying to test it for conductivity and magnetism and be unsafe with it. We could try to do magnetism from the outside of the jar. I think as we showed before, nothing doing. You may see something online that looks like mercury that can be manipulated by a magnet, but that is not mercury. That is ferrofluid. That's a little bit of iron floating around in a liquid substance like glycerin that kind of suspends it there. So looks really cool, but ferrofluid has iron in it, not mercury. Looks kind of like it though because it's floating around in a liquid. We can test the other two metals for magnetism though. This is our cadmium. Nope. Our zinc. Nothing. Not super exciting there. We can test them for conductivity. See if cadmium is conductive of electricity. We can see if zinc is conductive of electricity. So although these kind of stray a little bit from what we might consider metals typically, these are all metals, and we can check them out on the periodic table.
Zinc, cadmium, and mercury are all in the same group, the same column, the same family going up and down on the periodic table. They're all part of the transition metals section. They don't have a specific name for this column, for column 12. But we can just call it Group 12. They are all members of Group 12, and they likely have many similar properties as a result of that.